Now that we know each phase must increase the length of the shortest augmenting path by at least 2, we are now ready to bound the number of phases. Specifically, the number of phases used by Hopcroft-Karp is ordered square root of v. Note that the trivial bound, saying that there can be only one phase per possible augmenting path length, isn't good enough. That would still leave us with an order v bound. In reality, we will have a phase for length 1, for length 3, probably for length 5, maybe not for length 7, and so forth. But as we consider greater and greater possible phase lengths, the ones for which we will actually have augmenting phases get sparser and sparser. The key argument will be that after roughly square root of v phases, the path length will be at least square root of v, and that then will imply that we only have square root of v phases left. To fill out the argument, we'll let m prime be the matching found by Hopcroft-Karp, and we'll let m be the matching after the ceiling of the square root of v phases. Because each phase increased the shortest augmenting path by 2, the length of the shortest augmenting path in m is at least twice the square root of v plus 1, and hence no path in the symmetric difference between m and m prime, that is, augmenting for m, can have shorter length. This implies that there are at most the size of v divided by this shortest path length augmenting paths for m in the symmetric difference here. We just run out of vertices. There aren't enough left to fill out any more paths than this. And if there can be only so many augmenting paths in the difference, then m can't be too far away from m prime, certainly at most the square root of v. Hence, m will only be augmented square root of v more times, meaning that there can't be more than the square root of v more phases. We have square root of v phases to make all the augmenting paths long enough so that there can be only square root of v possible more augmentations. And that completes the theorem. Overall then, we've just shown that Hopcroft-Karp finds a maximum matching in time order e times the square root of v. We only had square root of v phases, and each phase, because of the clever way we were able to reuse the level graph, only ends up using order e time. And this result is actually the best known.